Welcome, everyone. Today, we step into inferential statistics, where social science transitions from simple observation to detective work. Up until now, we've described patterns in sample data, but now we ask, are these patterns reflecting true differences in the broader population? In this chapter, we focus on two cornerstone tools, the independent samples t-test and the chi-square test of independence. These tests allow us to compare group averages and categorical distributions while acknowledging statistical uncertainty. By the end of this presentation, you will know when to select each test, execute them, and interpret findings responsibly within social research contexts. Descriptive statistics summarize what our sample looks like, but inferential statistics allow us to draw conclusions about the larger population. Imagine asking whether women report higher depression than men, or whether college stress varies by geographic setting. When we observe a difference in our sample, say an average score of 2.1 versus 1.9, we must determine if that gap represents a genuine societal pattern or merely random noise from sampling variation. Statistical testing provides a mathematical framework to make that judgment call. However, remember that statistical tests only tell us if a difference exists. They do not explain why it exists. The independent samples t-test is one of the most widely used statistical tools in social research. It addresses a fundamental question: does the mean score of one group significantly differ from the mean score of another group? The key requirement here is independence. The individuals in Group 1 must be completely separate from those in Group 2, such as comparing Ohio University students with Ohio State students, or military veterans with civilians. Before sociologists can examine complex causal mechanisms explaining why groups differ, they must first establish whether a statistically reliable difference exists between group averages that cannot be attributed to chance. Let's examine a real-world example, comparing depression scores between women and men, measured on a 1 to 4 scale. In our sample, women averaged 1.83, while men averaged 1.76, a raw difference of 0.07 points. Running an independent samples t-test yields a t-statistic of 3.95 and a p-value under 0.001. because the p-value is well below 0.5 and the 95% confidence interval, 0.03 to 0.10, does not include 0, we reject the null hypothesis that there is no difference between the groups. We can conclude that women report statistically significantly higher depression. However, note that a 0.07 difference is quite small in practical terms, highlighting the vital distinction between statistical significance and practical importance. When software performs a t-test, it evaluates two competing hypotheses. The null hypothesis assumes the two population means are identical, and any sample difference is pure random noise. The alternative hypothesis asserts a true population difference. Software calculates the t-statistic and corresponding p-value. A p-value below 0.5 signifies that observing such a difference by chance occurs less than 5% of the time. Additionally, the 95% confidence interval provides a range of plausible values for the true population difference. If this interval excludes 0, statistical significance is confirmed. Researchers must always pair these statistical metrics with substantive evaluation of effect magnitude. Unlike the independent samples t-test, the paired samples t-test evaluates change within the same group of individuals measured across 2 time periods. Each person serves as their own baseline control. Common applications include pre-test, post-test evaluations, such as measuring student depression before and after an 8-week counseling intervention, or exam scores before and after a tutoring workshop. The test analyzes the mean of individual difference scores. The selection rule is straightforward. If you are comparing 2 distinct groups, use an independent t-test. If you are tracking the exact same individuals over time, use a paired t-test. Choosing the correct statistical test is one of your most critical responsibilities as a researcher. The choice relies entirely on how data were gathered. Always ask yourself, are these distinct groups or are these the same people measured twice? If you are comparing two distinct groups, like veterans versus civilians or men versus women, you must select an independent samples t-test. If you are tracking changes across time within the exact same individuals, such as pre- and post-workshop exam scores, you must select a paired samples t-test. This table on this slide summarizes this decision rule. Now let's switch gears to the chi-square test of independence. While t-tests require a continuous quantitative variable to calculate averages, chi-square tests evaluate relationships between categorical variables. Instead of group means, chi-square counts how many subjects fall into specific category cross-sections. The test compares observed counts, what we actually collect in our sample, against expected counts, which represent what we would mathematically expect if no relationship existed. A small chi-square statistic means observed counts align closely with expected noise, whereas a large chi-square statistic indicates a meaningful relationship between variables. Here is a standard cross-tabulation comparing gender and depression categories. Here's a tip. Always examine column percentages before reading test statistics. Percentages reveal direction. 58.3% of women report depression symptoms compared to 37.5% of men. To verify if this 20.8% gap is statistically significant, we check the chi-square results. Chi-square equals 8.66 with a p-value of 0.003. Because the p-value is less than 0.5, we can conclude that this difference is unlikely due to random sampling chance. Remember, percentages describe the pattern's direction and size, while the chi-square test determines statistical significance. A primary advantage of chi-square is its ability to compare multiple groups simultaneously. In this study of 2,824 students across 5 racial categories, for instance, high depression rates ranged from 46.2% among Caucasian students to 58% among Asian students. Pearson's chi-square yields 9.74 with 4 degrees of freedom, and p is equal to 0.45. Because p is less than 0.5, we conclude a statistically significant association exists. However, notice 2 key nuances. The percentage differences across categories are quite modest, and chi-square only tells us a relationship exists somewhere. It does not pinpoint which specific groups differ from each other. To wrap up Chapter 6, use this decision matrix as your study guide. When comparing averages between 2 separate groups, choose the independent samples t-test. When evaluating changes across time for the same individuals, use the paired samples t-test. When analyzing relationships between categorical variables, use the chi-square test. In our upcoming chapter, we take the next logical step, moving from group comparisons to examining associations between 2 continuous quantitative variables using scatter plots and correlation coefficients.